Section 3.3 looks at how the first derivative is related to the graph of the original function. Specifically, we're going to be looking at increasing and decreasing functions and what we call the first derivative test. You'll recall that we talk about an increasing function is when the graph is going up from left to right, and a decreasing function is when it's going down from left to right, and a constant function is when the graph is level. Now, you may have noticed that those terms, while they're descriptive, they don't sound very mathematical. So what we're going to do now that we know some calculus is we're going to go in and we're going to replace those kind of working definitions with a definition that is based more in mathematics. And so what we'll say here is that a function is increasing if the derivative is greater than 0. You can notice over here we have this one area from b to c where this function is increasing, and if we drew a tangent line, like I've done here, to that function in that area, that tangent line is going to have positive slope, which means, of course, derivative is greater than 0. Okay? That means, of course, then also that if the derivative is less than 0, we're looking at a function that is decreasing. This particular function is decreasing from negative infinity all the way until we get to a. See, if we draw a tangent line, we get negative slope. And then again, when we go from c to infinity, we would have decreasing function because the slope of the tangent line would be negative, or the derivative is negative in those two regions. Finally, we can talk about a constant function, and that would be somewhere where the derivative is equal to 0, so the function just levels out. And we don't really actually have a good tangent line because the line goes just straight through the function. But you can see all the way through there because the function is constant, the derivative is equal to 0. Right? Now, if we want to determine the intervals, then that the interval is that the function is either increasing or decreasing, the first step to doing that would be to take the derivative. Once we've taken the derivative, we're going to find any critical numbers, any places where f prime is 0 or undefined. Then we're going to draw a number line, divide up the number line using those critical values that we found from the derivative. And once we have our number line divided up, we can just plug in any value from each section of the number line, and we can find out whether the function is increasing or decreasing on that interval. So you see here on the right I have an example. 2x squared minus x cubed is our function. If I take the derivative, again, that's pretty easy. That's 4x minus 3x squared. I take that, I set that equal to 0, and when I do that, I get x could be either 0 or 4/3. Now, I would also want to consider any places where the function is undefined, but of course we know that polynomial function defined for all real numbers. So we don't have to worry about undefined. We've got these two places where the derivative is equal to 0. That's at 0 and positive 4/3. Once we know those two places, we divide up our number line at 0 and 4/3. And then we just pick a number that falls in each piece of the number line as we've cut it. So we cut the number line, we have one piece that starts at negative infinity and goes to 0, another piece that goes from 0 to 4/3, and finally from 4/3 to infinity. We can pick any number in there we want. I always try to go with the easiest one. So if I want a number that's less than 0, -1 seems like a natural option. So I take -1, and notice I am plugging this into the derivative. This is something different from what we've done in other tests. We plug it directly into the derivative, not the original function. And when I plug -1 into my derivative, -1 times 4 is -4, and -1 squared is +1, times -3 is -3, so -4 minus 3 is -7. So notice that I have marked here that on this interval the derivative is always going to be negative. If it's negative at one place, the only point it can change is at a critical point. And so that whole interval from negative infinity to 0, that function has to be decreasing. Then I choose a number in between 0 and 4/3. And so we know that 1 is in between there. I could have picked anything I wanted to, square root of 2 divided by 2 if I just felt crazy. But 1 sounds like a nice easy number. I take 1, I plug it into the derivative. 4 times 1 is 4, minus 3 times 1 squared is 4 minus 3, which gives me 1. Since it is a positive 1, then I know that all the way from 0 to 4/3, this function has to be increasing. And then I have, so I just put little plus signs in that interval just so that I know that the derivative is positive there, so that function is increasing. And finally, I do the same thing with a number greater than 4/3. 2 sounds great, so I take 2 times 4, I get 8. And 2 squared is 4, 4 times 3 is 12, 8 minus 12 gives me negative 4. And so I see that I have another interval from 4/3 to infinity where this function is decreasing. Now notice that the critical points are the only points where the derivative could change from positive to negative. That doesn't mean it has to change at a critical point, but those are the only places where it could change. So that's why we divide the number line up in that way. So now a very similar test is called the first derivative test. It's really, we're doing the same thing, but we're trying to gather just a little more information from this test. So what we're going to do for the first derivative test, the first derivative test is going to locate for us relative maximum and minimum. So you will remember from the last section that relative maximum and minimum have to occur at a critical point, at a critical number. So we start by taking the derivative. This time we're going to find all the critical numbers, but we really only care about critical numbers where the original function is defined. If the original function is not defined, if it's not continuous at that point, then remember it can't be a relative maximum or minimum. But if the function is defined and the derivative is either 0 or undefined, then we're at a point where we could have a maximum or a minimum, relative maximum or minimum. So we take the derivative, we find those critical numbers where the original function is defined, and we divide the number line up just like we did in the last little bit. And finally we plug in one value, we see if the function is increasing or decreasing. So I've used the same function here, so we don't have to go back through all of that process. All of that is basically the same. We're just doing what we did. We're just going to glean some more information from what we already did in the last slide. So what we will see is if we're at a critical point and the f prime changes from positive to negative. So let's look here at 4/3. Because notice that at 4/3, the derivative changes from positive to negative. See my little plus and minus signs? Changes from positive to negative. If we imagine that on the graph, of course positive means increasing, and negative means decreasing. And of course at 4/3 it levels off for just a second. And you can see that what we would get is a relative maximum. Likewise, if the sign changes from negative to positive like it does at 0, then we can see on the left-hand side of 0 this function is decreasing, on the right hand it's increasing, and so at 0 where it levels out for just a second, that's where we get a relative minimum. And finally, if we had a critical point where the sign did not change, that graph, obviously this doesn't happen in this function because we have two critical points. One's a minimum, one's a maximum. But we do have sometimes a graph that looks something like this where it just levels off for a second, but then it just keeps increasing. And in that case, we have a critical point, but it's neither a minimum nor a maximum. So if the derivative does not change sign, then we don't have either a relative minimum or a relative maximum. So that's the first derivative test, and it helps us to find those critical points. So on the next slide, I'll give you a few problems that you can start looking over, and we'll work on these in class.